and welcome to my presentation on SuanMing, our approach for explainable prediction of performance degradations in microservice applications. My name is Johannes Grohmann, and this work was conducted together with my colleagues from the University of Würzburg and Huawei Technologies in Tel Aviv, Israel. So the context of SuanMing is basically a reactive monitoring stack. So imagine we have a microservice application running in the cloud, and we monitor it via Pinpoint, Kika, Zipkin, or other tracing tools. Then usually we get a lot of tracing information, and as you can see here, we have different call chains. We have also logs and maybe some information here. But the problem is that we have only reactive monitoring here, so we need to rely on this reactive monitoring. And this is suboptimal because if we have, for example, a performance problem here that decreases the user experience and we are reactive, we can only apply the reaction itself after, for example, this user experience threshold is crossed and after we notice that the problem actually occurs. And since we have usually a delay from when the action is conducted to when actually the effect comes into place, we usually have this user experience valley here, which we see here in this example. So the idea is, if we move this reaction more into the future, basically, if we can do this reaction earlier, then we can maybe avoid to fall below the user experience threshold in this case, and therefore improve the overall experience of our users from the system. So now the question is, how can we do this proactive monitoring? So there are basically two areas focusing on this. First of all, we have the root cause detection approaches. These are a set of approaches that can work with the tracing information that we have to basically detect the performance problem that's currently occurring and therefore avoid it. But again, as we just said, we don't have any forecasting here. So no prediction, actually, no proactiveness. And the other sets of approaches that do actually prediction of performance degradation, they usually require detailed information. So that's what we don't have because we just rely on the tracing data. So our approach or our contribution can be found in between here. So we do root cause detection on the one hand, because this is important for actually solving the problem, for reacting to the problem. And also we do performance prediction so that we can act before the problem actually occurs. And we do this without requiring the additional information or a priori knowledge about the application. So yeah, quickly to summarize our assumptions. So we call our approach SuanMing, and we want to augment these existing monitoring stacks with the proactive components. We assume that we are talking about microservice application, that we have application traces available, but no other knowledge about the application. And our goals are to achieve high explainability of our predictions, because this will then help us to avoid the predictions in practice, to achieve a low number of false positives, and to be modular and extensible from our architecture approach. I quickly want to summarize what we want to achieve in a nutshell. So we have state-of-the-art reactive monitoring, which we want to enhance by enabling prediction and proactive applications. Therefore, we have the power to avoid performance problems before they actually happen and get noticed by the user. And now I will present our approach for a four-step prediction process. So let's first start with the general architecture. So we have users, and these users access services in our application. This might be two different REST services. And usually in microservice applications, we have not only those services, but those they are calling other services that are back in the chain. And one of these symbols here, or one edge here, basically means that service B sends requests to service D in our example. So this is our basic architecture for our example that we use now. We have a few services calling each other and also crossing sometimes. And yeah, now the first step would be of the SuanMing approach is to forecast the actual loads of the user. So we predict that in the next time interval, we get 30 requests of at service A and 60 requests at service B. This can be done with classical forecasting, time series forecasting engines. Now, what we want to find out is we want to do the request propagation. So if we know that there are 30 requests coming into service A, how many requests will be going into service C, E, or H? And we see that we propagate these requests here. So this might be 30. So for every request, you get another request here. And then every request on E on average issues 2 requests here for service E, and so on and so forth. And then in third step, we do the performance inference. So now we analyze, is service H able to handle 80 requests per second, or would that be too much? Or is that fine? So we do this based on a binary labeling. We say green, so for service I, it's fine. He can handle 90 requests, so 30 plus 60. But service H, for example, would be overwhelmed with this 80 requests here. And then we would actually take the performance of service H, also use it as an input for service E. So we know that service E uses service H. So we need to calculate what the response time of service E would be if we do 60 requests input and have a bad performance of service H. And in this example, we now would receive some back propagation like this. So we have bad performance that propagates all to service A, where the user actually notices. So in this step, now we have the opposite, meaning basically now an edge from service B to D means that the performance of B depends on D. So we start with the backend services and now propagate the expected performance into the front for the users. So now that we know that service A has a performance problem, and also that the user sees this performance problem, the next question becomes, what service do I need to fix? So what's my root cause here? And how we would do this is, for example, we have service A, we know it's a bad performance. Now we would pretend that service C is actually having a fine performance. So if we pretend that service C is green, what would happen to the performance of service A with these 30 requests in this example? And now we would see that, for example, service A would become green. So then we know, okay, service A is not our performance problem, but instead service C, for example, is maybe our root cause. And now we label this as non-root cause. If we do the same for service C, we see, okay, it's also not the root cause, service E the same. And finally, we arrive at service H, and now know that service H is our root cause, because I cannot go ahead and label its dependency green. So therefore, H is the dependency that we need to fix actually in order to get the whole application to the green state again. So the architecture of our approach is split into several multiple components. We have the tracing data coming in here. First, we have a provider component that takes care of data aggregation and data cleaning. We store the data and then feed them into the propagation, the performance, and the load forecast trainer. And these produce the models that actually we just saw in the prediction step, where we go ahead and have our 4-stage prediction process. This needs to be done based on the models that we learned here in these components. And then finally, we forward the prediction to the analyzing component, which takes care of the root cause analysis that we just saw. And in the end, the framework can return predictions and ratings of the states as we predicted them in this example. Okay, so let's go to the evaluation. So our test application is Terrain Ticket, which is a fairly large microservice demo application. We have 42 different microservices, 38 of which are monitored by pinpoint and which we use for this evaluation. And in Terrain Tickets, it's about buying, booking, and reserving tickets for a railway company. So the workload is 512 users randomly logging, searching for for trains, booking them and then collecting them in the station. And here we also inserted some legal, illegal requests and some variation with the food and the reservation bookings. So if we look at this application, we want to find out, okay, are we able to correctly predict the state of a front-end service independent of a problem at the back-end service? So what we would do is we have a green application, and now we intentionally stress one back-end service, in this case the train service. And what we want to observe is that all these dependent services here, which directly or indirectly call the train service, are now experience performance troubles. So if we, for example, look at the travel service here, which calls the train service, we see exactly that. So in this example, we have in blue the arrival rate over time. So we have an experiment of 1 hour here. And as we see, the arrival rate to which is the blue curve here, to the train service is fairly low and also quite noisy, but fairly constant. So we see that we get some spikes here and there, some drops here, but overall the performance, the arrival rate is quite average. But in the red curve down here, we see that the actual performance is really not that constant, because we have high spikes at mostly regular intervals from, let's say, 200 to 300 milliseconds in normal responses to over 6,000 milliseconds. So let's say 20 times the normal response time. And this is, of course, based on what we did with the train service here. So these are actually the timestamps in which we stressed the train service in order to see effects as we travel. And this is exactly what we see here. So okay, so now we achieved the desired effect in performance here. Now we want to see if actually we are able to also predict this effect. So in this case, we have the measured performance in blue and the predicted performance in red, and one model type that we used. And as we can see at the start, as we start with no application knowledge, we don't do any predictions. And then here also we massively fail in predicting the actual load spike. So please note that this is shifted to the left. So actually all the predictions occur obviously before the measurements, but we just aligned them in order to make it more visible what's actually happening here. So if we would have a nice prediction here, that would be at the same point here, but as we see, we are way too late. So actually there's no possibility to react here. But this makes sense because we don't have any application knowledge yet. And as we see, the next spike is captured better, and then we continue to learn the application and become better and better. Here, for example, at the end, we also can see that we are way less noisy than, for example, than the measurements actually are. So the model actually gains some robustness, and we can see that it's able to capture these spikes and predict these spikes beforehand. But we can also look at some numerical analysis here. So first up, let's concentrate on the top here. We have our approach, which achieves a symmetric mean absolute percentage error of 0.2, while a mean regressor, of course, is way worse with almost 0.7. And we can also see the same at the mean absolute error in milliseconds. And we also added here another approach, which is the optimal forecast. So this is the performance of our approach if we do no forecasting, but actually use the real-life monitoring. So if we get the optimal forecast values in, then we see that we can also decrease the error a bit more. So we can actually improve the performance by improving the forecasting, which is a nice observation here. And now we also see the labeling that we just had. So we differentiate between true positive, false positive, true negatives, and false negatives. And these lead now to accuracy and F1 scores that we can analyze. Also, next to the optimal forecast, we added some all green and all red classifiers, which, as you can see here, predict always green ratings are always fine, or always a red rating, so always problematic. And they, of course, achieve way lower accuracies than we do with our approach, but we are also able to beat the mean regressor and some random approach here that just predicts randomly the classes for each interval. And as you can see here, still the optimal focus is able to achieve a bit better performance. So we can actually see that this drop here is basically due to the model error, while the difference between the F1 score of 0.8 and 0.6 is the forecasting error. So we have this nice distinction here where we can see, okay, which are the models that we actually need to tune in order to improve the performance here. But overall, we can see that we have an accuracy of over 0.9, so over 90%, or almost 96% for the optimal forecasting. So that's actually quite nice. And also, if we generalize this to the whole application, not only the one train endpoint, we see that the accuracy even increases because most of the applications, the services of the applications actually do not experience any performance problems, right? So we actually also see that all green performs quite well here, because actually most of the time the performance is really fine, which makes sense because we basically aim at detecting problems here which are not the norm, but we still see that we can have a very good F1 score in comparison to the all green, for example. And we also measured a bit of the overhead. So we see that we took on average 226 milliseconds. That is also fine for doing reactions, because the latency is very small. And also the training per endpoint is around 7 seconds. So we believe this is fine. And we also tried a different application, in this case, the T-score microservice applications, where we could achieve similar performance values to the slightly bigger train ticket store. All right, so for future work, we aim at basically 4 different things. So this is our current state, let's so to say. So of course, it's always better to increase the forecasting horizon in order to move this reaction a bit more back, so then we can react further and maybe are even better. Another important aspect is the tuning of the monitoring granularity. So we didn't cover this in this talk, but basically you can have 5 seconds or 20 seconds of prediction intervals, which of course also influences the horizon here and the capabilities that you have. Also, it would be nice that these predictions here actually report on what to do with the issue. So right now we know the service, but we might want to know, okay, we need to increase the RAM of the service, increase the CPU of the service, whatever. And finally, it's also nice to have an automatic threshold detection here. So seeing, okay, when do I actually need to start reacting here? So these are the targets that we could go for in future work. But for now, let me quickly summarize. So we wanted to augment the reactive monitoring with a proactive component. We did this by applying our 4-step prediction approach, basically evaluated on the train ticket store, and saw that we could actually achieve really nice results for the travel service. And yeah, I just want to quickly show references here before I conclude my presentation now and say thanks for your attention and thanks for listening.